Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. I am going to cheat a little bit, and I'm going to start with a little bit of what might be deemed lecture, so sorry about that. It's really kind of combining stuff that we've already done, so at least that's how I'm assuaging my guilt. But I'm going to start with reminding us that, at least as far as the non-relativistic cases go, the kinetic energy goes as half mv squared, and the magnitude of momentum goes as m times v. I can take this kinetic energy equation, half mv squared. I can multiply top and bottom by m, and half mv squared becomes 1 over 2m times m squared v squared. But m squared v squared is really just p squared, right? So the kinetic energy classically goes as p squared over 2m. No magic in that. And so I also ask that you recall from our lab a couple weeks ago that the Compton wavelength is h over mc, and from lecture the other day, this de Broglie wavelength, lambda goes as h over p, where p is momentum. And so we should also remind ourselves that we got this in our discussions of special relativity, that E squared is quantity PC and quantity squared plus quantity MC squared and quantity squared. We can write that as quantity PC and quantity squared plus ER squared. We can also remind ourselves that in this regime where we don't have to worry about potential energies, the total energy is just this rest energy plus the kinetic energy. So if I take this and I sub in for E squared, I get that ER plus EK squared is equal to P squared C squared plus ER squared. Multiplying this out, I get ER squared plus 2ER EK plus EK squared. But I also have an ER squared on this side, so if I subtract across, the ER squareds take care of each other, and I'm left with solving for P. P is equal to 2ER EK plus EK squared to the half, all divided by C. So far, so good. And then if we remind ourselves that lambda is h over p, then lambda should just be h divided by this stuff. If I do that, I get h times c over that stuff, quantity 2ER EK plus EK squared to the half. I'm going to play a little trick here, and I'll remind us that the ER is mc squared, the rest energy is mc squared. I can take this and divide top and bottom, the numerator and the denominator, by mc squared, which is the same as dividing by ER. So the top I'll divide by mc squared, the bottom I'll divide by ER. The nice thing about this is the numerator becomes h over mc, which you probably recognize is this Compton wavelength. The bottom, bringing this ER inside the square root, becomes 2 times quantity EK over ER and quantity plus quantity EK over ER and quantity squared, all of that stuff raised to the half power. And so now, since we've identified that we have a lambda c, a Compton wavelength in the numerator, I can divide across, and what I get is lambda over the Compton wavelength is equal to 1 over quantity 2 EK over ER plus EK over ER quantity squared, all of that stuff to the half. So far, so good. So let's see if we can make use of this. This has kind of a weird shape to it. this is really not doing it justice, but this is often plotted on a log-log scale, but it has kind of that feature to it, if you squint. So let's see if we can make use of this. So if we have some detectors on our spaceship, and we observe a cosmic ray proton traveling super fast, has a kinetic energy to be 150 giga electron volts. If we wanted to calculate the de Broglie wavelength, then what to do? Well, we can remind ourselves that the rest energy of our proton is 0.938 giga electron volts, 938 mega electron volts, or 0.938 giga electron volts. And we have this kinetic energy, right? And so we can get to EK over ER is going to be 150 giga electron volts divided by 0.938 giga electron volts is, pardon, 150 divided by 0.938 is, I'm getting 159.
I got 159.9.
159.9. Let's round it to 160. And so if we were to plug that in to this equation, I'm probably going to regret this, but I'm going to use 160. So 160 squared plus 160 times 2 is 320. And then I'm going to square root this. And then I'm going to invert this. I'm getting 0.006. Is that roundabout to what I've previously gotten? It's not. Where is my fatal flaw? So plus 320. I'm getting about 0.006.
Yeah, I got that. Yeah, I got a 6.2 times 10 to the negative 3.
Sorry, what are you getting?
6.2 times 10 to the negative 3.
Yeah, that's what I'm getting also. So I am going to assume that I am not totally off base here and that I just screwed this up when I tried this in my notes. If we were both getting the same answer, how can we both be wrong? That's never happened in the history of things. And so we could, you're getting that lambda over lambda c. We are both getting, I won't throw you under the bus, 0.00623. Okay. And I will template this even though most of this is clearly not working for me. We can remind ourselves that lambda c is h over mc. So 6.626 times 10 to the minus 34 joules seconds over 1.67 times 10 to the minus 27 kilograms times 3 times 10 to the 8 meters per second. So lambda c for our proton I'm getting about 1.32 times 10 to the minus 15.
Yeah, that's what I got.
Okay. So, and that is actually what I had, so clearly I just screwed this one up. For some reason in my notes I have this as being 3 times smaller, and I don't see my factor at 3, so I'm going to assume that I just screwed it up. And so if we want to know the de Broglie wavelength then, well, lambda should equal to lambda c times 0.00623. And so if we took 1.32 times 10 to the minus 15 meters, we multiply by 0.00623, I'm getting about 8.2 times 10 to the minus 18 meters, which is tiny, right?
Yeah.
The size of the nucleus of an atom is on the order 10 to the minus 15 meters. And so, you know, this is smaller than the nucleus of an atom. So, I'd feel better if that matched my notes a little bit better than it does, but oh well. Yeah, I don't know what I did wrong there. Okay. That aside, this is the effective de Broglie wavelength for our very high energy proton. So let's return to maybe some semi-classical stuff. And so I want to look at uncertainty, but I'm not going to go full quantum mechanical uncertainty here. I'm really just going to kind of dip my foot back into this and think about this in a classical sense. And so this is definitely macroscopic stuff, not quantum mechanical. But you can imagine standing at the center of a 20-meter long pier, and you count 15 wave crests. I don't know if that's really 15, but was my aim. Between the two ends of the pier. And we want to have some sense as to what a classical uncertainty in the wavelength is. And so classically, you might describe this as just the wavelength, lambda, is equal to 20 meters over 15 waves, is 4/3, is 1 1/3, so 1.33 meters is the wavelength. Yay-ish. The spatial, so here, I'm going to give us kind of our classical statement of what we mean by by uncertainty in wave measurements. And the uncertainty in the wavelength times the uncertainty in the spatial extent is on the order of the wavelength squared over the angular extent of the wave. And so here the spatial extent is 20 meters. And so we could say that delta lambda, just mimicking this equation, goes as lambda squared over 2 pi delta x. And I should keep that as squiggly equals. And so if we go with 1.33 meters squared over 2 pi times 20 meters, and I'm getting about 0.014.
That's what I have.
Awesome. Which is a little more than a centimeter, right? And so what we would probably want to do is say that this wavelength is 1.33 meters with a minimum uncertainty of about 0.01, 0.02 meters. Is that all right? And so we are going to extend this in our next lecture to this idea of our newfound wave function describing the probability of locating a particle. We're going to start with something very similar to this idea, and we're just going to kind of broaden it to give kind of the very, very famous uncertainty equations. So, and you can write them in terms of delta p and delta x. So that will be coming up shortly. In fact, you might be able to anticipate that since we have kind of come to expect some relationship between p and lambda. And so an uncertainty in momentum is also an uncertainty in wavelength. And so we might be able to write something on the order of, instead of an uncertainty in the wavelength, an uncertainty in the momentum times an uncertainty in the position is going to have to exceed some minimum value. The minimum value is going to look a little different, but at its core, it's a similar idea. For this one, I think we are all set. The last one is going to take us